All right. Okay, so we're going to change the plan a little bit. I will try to keep my lecture a little bit short, so we have a little bit more of the hand-on exercise. And today, hopefully, we can do a little bit about the effective mass, the second set of the notebook we had yesterday. And you probably don't have time to finish this calculation, but if you like to play a little bit more, so the pre-class is a little bit like thinking about the concept, how to do that, and do a simple analytic example. The second set is like playing around with the data by itself. So a little bit more programming there. So it really depends on your background, but no hurry, just kind of make sure you understand along the way. And tomorrow I will try to keep the parton distribution discussion a little bit shorter. Hopefully I can keep it under 20 minutes. And then we can do a little bit about the structure. So a lot of time when we try to study the structures, we do a lot of very similar exercise that you will see, something called three-point function correlators, and we vary the operator. And you're going to see a little bit in my talk, some of my presentation today. In very different operator, you can get different structure that corresponding to different physical quantity. And it's kind of really fun by just thinking about those problems, right? All right, so let's go ahead. So one of the big topics in QCD really try to study some of those QCD particles that you will learn from the games and their substructure, right? And how do you do that? You know, we are all familiar with, you know, we need some sort of telescope and we need some sort of scattering, either with the light, which is the most typical case that you saw in high school. And then you see the substructure, and then you can actually, from learning those structure, we can do more exciting science, right? And so you want to see something smaller, you just have to build much bigger telescope. So you're going to have a very exciting tour tomorrow to see the very, very powerful high energy telescope that's going on at Jefferson Lab. And there are a bunch of different processes. Those processes, it's still like scattering. Instead of using light, you might be using electrons or other particles so that you can see more complicated, something that's much smaller scale, higher energy, so that you can kind of knock out the nucleon and then see what happened there. And then we learn from that. By studying the post process, we kind of reconstructed the structure of the most commonly proton, and some of the experiment you're going to see there that's doing pion. And I don't think there's a kaon experiment yet, but they are various different exciting program going on, right? So in those cases, like the physics is actually, you can think about you are like a detector based, yeah, you're like a detector, right? Like a police detectors. There are certain things happen, but we don't know what happened in the process. So you kind of look around all those evidence, and as much as you gather as much information as you can, and you try to backward reconstruct a lot of those information as possible, right? And then this is going to be related a little bit about what I'm going to talk about tomorrow. So we're going to have a number of matrix elements, and we try to construct something that's like a universal quantity that we don't know what they are about, but we try to reconstruct them as much as possible. Right, and so how do we do those? So like I mentioned yesterday, so we were taking a bunch of snapshots of the QCD vacuum that were best describing the ground state for the QCD, right? So that's something we're familiar with, right? And this have various different gauge and fermion actions, right? So you can write down different gauge action. You can have more than one kind of gauge action on the lattice because we have additional degree of freedom lattice spacing. And as that go to zero, right, everything will recover to the central ground state. And similarly, you can do that with the fermion actions. And we do those depends on the, you know, what particular collaborations main business interest. Some there are groups that are really interested in chiral symmetry, so they want to preserve that chiral symmetry in final lattice spacing, even though when A go to zero, the whole chiral symmetry recover exactly the same as continuum. But for them, it's a lot really important to have very nice, clean measurements. So they want to preserve that symmetry. And you pay the price for introduce additional term that might increase your computational resources, right? But then you can also think about it, so like often we had to think about between trade-off of statistical error and systematic. If you have much better systematic, even though the computation is more expensive, but you don't have to spend a lot of time worrying about, oh, there might be unknown sources somewhere. I don't know how to estimate and all that, right? So I talked to some of you yesterday, a lot of time when we do research, we are like spending a lot of time thinking about the error bar, right? So unlike classes, you just like be able to get a number and that's the end. If a number come out to be close to what the design problem is, that's sort of the end of the story. But in research, you're going to spend a lot of your time, your PhD years, probably thinking about the errors, right? If you are constructing the model, you might want to construct a model with error as small as possible or close as continuing the real world as possible. When you make approximation or when you do experiment, there's always those concerns about, how do you control those systematic that some of them some of them you might not know, and where that can show up and mess up your result. So we spend a lot of time thinking about that. So that's like, for me, that's a very different transition from being an undergrad to grad student, just so you have to start thinking about those, right? And sometimes we don't know the answer is, right? Then you have to you kind of have to convince yourself you're doing every step that's all correct, especially your number sort of controversial with other people's, which happens. There are experiments happen here, something called proton radius, right? People just assume this is more than a decade ago, people, when they were doing experiment, they was like, oh, fine, they're just going to confirm what we already know, right? And then it turns out the radius turned out to be very different. And that become a really big field of discussion of what else is out there that we don't understand and so on. So there are a lot of processes like that. I don't know how I get from here to there. But and another thing I want to mention, somebody asked me the question about why do we call QCD vacuum ensemble gauge configurations? So it did occur to me yesterday. So in early day of the Lattice QCD calculation, it's really expensive to put fermion degree of freedom there because fermion has spin, color, and then you have all the size. So you have a lot more degree of freedom than gauge field, which is just a SU3 fields, right? So in the early day of simulation, people do start with you want something simple that you can analytically calculate them to verify your calculation is correct to SU2 gauge, before you go on to SU3 gauge. So I think in early days, most of the QCD vacuums gauge field only, and probably that's where the gauge configuration name come from. And then since we started adding fermions, the language already is established, so we just continue calling that, right? And then you can have, I say, the fermion is expensive, so we don't always add all the possible flavor, right? So the most important flavor on the hadronic physics is aqua and down quark that play important roles. In some physics, the strange quark can also have very important role coming up. Like you study the strange structure of the proton, or you study the particle that involve a strange quark, and the strange quark can play an important role there. And then so you have sometimes you have up quark, down quark. We usually do ISO. We have up quark, say the up quark and down quark masses should be about the same. So they are very, very small isospin symmetry breaking there. And then you have 2 flavor plus 1 with a strange, or 2 plus 1 plus 1 with a charm, right? Again, depends on the physics you are interested in. And then you have variation of parameter in terms of the pion mass that can vary, and lattice spacing that can differ as well, and then the value of the calculation. Right. And then you create, say I want to study protons. I create proton in one space-time, and I kill it in another space-time. So again, this is like a 4-dimensional QCD vacuum where this direction, horizontal direction representing time, and there are some XYZ direction there up to your imaginations, right? And so they are propagated going on. They are complicated. There are a lot of gluon and vacuum interaction that we are not drawing here. And then so if you want to study the structure of the protons, then you will try to put in a plot, right? So it's like when you are studying electric fields, you want to know how much the voltage are, so you put in the plot in the proper different places. And we do something like that, right? But on the computer. So we put the different insertion time, and then we try to study the time dependence. And from there, we try to extract some of those matrix ornament that give us various different quantities, right? So we have things like quark propagator. We need to invert using supercomputer. They can be bigger than roughly, I think today we roughly work somewhere about 10 to the 12, and it's just going to get bigger and bigger as the calculation will get more serious, right? And then, so once we have those time dependence, right? So we're going to do this exercise tomorrow in the set 3 notebook. But roughly is like one of the things we need to be careful is sort of try to make sure that we get the true ground state, right? So I mentioned briefly yesterday, you put in a quantum number. That quantum number can overlap with any of the same radiating excited ground state that have the same quantum number as well, right? So if you only care about the true ground state and you want to make sure that some of those excited state that is written as a 1 as a first excited state, second excited, and so on, is not coming to for the contributions, right? So there were quite a bit of, like about 10 years or so, people were trying to understand some of this discrepancy when we are studying something called axial charges, and that has some significant differences from what experiment solved from the neutron decay. And so that turned out to be excited state systematic is not under control. And the reason we do that is so that as you go, obviously we want this separation to be, we want to study the dependence of this separation. So you can control that parameters. But as you get the separation larger and larger for the case of nucleon, the signal get worse, right? So when you have a limited amount of computer resources, right? Usually what we do is we study a small sample of statistics to try to determine what would be the best optimal operator to run, right? And so the problem with a small statistic is the error bar is going to be bigger. So you may not, there might be something that turned out to be quite different when you do like a 10 million measurement, but you don't see them in the first 1,000, right? Because the error bars are over there. You'll be like, oh, no, I don't have to waste my time doing all those bit separation, which contribute a lot of noises here. So here is one of such example, right? So where I center the middle of the separations and I slowly increase the separation. And this is like a last measurement. Now I can see if I assume this is all agreed, you can actually get very different true ground state, which is somewhere about the middle of the plateauing. That's why we draw the this way, right? So you can tell it's actually quite different as I increase the separation, right? And this band is sort of, if you just start to put in the excited degree of freedom and do something a little bit more complicated, and you do see we do have like, the true ground state will be here if you include those degree of freedom. And then as you use more data, you reduce the total error, which is great. And then even when you don't have the resources doing so, you just get something a little bit bigger error bar, but you are at the right place. So that's some of the things that we have, almost every collaboration doing that now, even though, yes, you still get much smaller error when you have small separation, but we do want to study a few of them, and then include the excited state in the analysis. So even though you get the bigger error bands in the result, you still have a consistent analysis across different ones. Yeah. So right. And then after you get all that with the structure, we often had to do something called renormalization. And for those who done quantum field theory classes before, renormalization is really not a fun thing to do in QED, definitely very not fun thing to do in QCD, and definitely even less fun to do it on the Lattice QCD, because now you break additional degree of freedom, right? So there are some non-perturbative way to do this on the lattice. They match to continual and S-basking, which is a common way of renormalize the operators. And because at QCD, you often have to ask what is the scale that you calculate on the for particular quantity. And most of the quantity, if I didn't mention, is roughly at the 2 GeV, just some sort of conventional scale that everybody report their number with. So if we don't mention the scale, it's in NS bar as one of the renormalization scheme in the QFT, in case some of the undergrad haven't taken that yet. And that's usually about 2 GeV, right? And on the lattice, we had to control our own systematic, right? So we had to measure the pion mass. If it's not directly calculate physical pion mass, we should do multiple of them and extrapolate the physical pion mass and measure the value. It's not affecting our result. And lattice spacing, if we can, do multiple of them so we can extrapolate to the continuum limit. And only then we can control the monster that's potentially living in the Lattice QCD, right? So a lot of people will tell you, yes, Lattice QCD is ab initio and everything, right? But any method, right? It's not just Lattice QCD, any method, right? You come with zone systematic, you have to keep that under control so that you can say, oh, I'm actually getting the right answer to compare with experiment and of course different methods and so on, right? So here is one of the example I did with a collaboration called PNDME. So we are trying to do try to have a very precise coupling constant so that we can use that for new physics prediction and so on. So we had to control those systematic errors, right? So I just want to show you example, like, so typically if a good calculation will have multiple lattice spacing, right? Hopefully at least a factor of 2 differences there. You will have different value. And the value is really depends on how big your pion, how heavy your pion mass is, right? You can imagine the heavier the particle, they doesn't move as much, so they don't need as big value, right? As you go to lighter and lighter pion masses, right? You need the value to be bigger, right? And that's where the calculation get more expensive as well. So therefore, the empire law is usually another way we describe the value rather than the absolute value by itself. It should be some sort of dependence on the pion mass, how heavy the quark is itself. And then you have different pion masses, and hopefully some of them with the physical pion mass, multiple separation, and should be have a lot of measurements, right? So basically, this is like how many times we repeat. We take the example and repeat lots of calculation in different source location and moving on to keep them as independent as possible, right? And then, so for example, here's an example of the tensor charges. And so you could have that inserting prop with an operator, with a gamma matrix to be a tensor operator, and then you can get the tensor charges. So that's the simplest thing that we can do, just a coupling of the hadrons. And so again, so here's just an example results. You will have repeat the same calculation many, many times, and you will have some statistical error and systematic, and you have multiple pion masses, different values, different lattice spacing, and you do a simultaneous extrapolation. Here's just one of the naive forms. Sometimes you can use chiral perturbation theory as a guideline to have very more complicated form, but it's just an idea of how to do this, right? So then you simultaneously, which is this pin band here, right? Simultaneously extrapolate to pion masses and A equal to 0, and then value infinity. In this case, you see it kind of plateauing. So in terms of the value dependence layer, right? And then, and then often is you need a higher precision. Basically, you sort of continue doing such a calculation, adding more physical pion mass, and increase all the statistic as well, and then come up with slightly better calculation and so on, right? So these are very similar procedures. And so there are a lot of collaboration. So for the charges is one of the most calculated quantity on the lattice. And in tensor charges, there have been some interest since about 2012. Before then, people will be like, why do we calculate this quantity? There's no experiment number that we can compare, because measuring the tensor charges involve something that require experiment to do something called transversity, which I'll talk about that tomorrow. It's a parton distribution function. And you have to have very good measurement of all that, and you do the integral to get the tensor charges. While lattice calculation itself, because the field theory definition that we can get tensor charges directly as a one number rather than multiple experiment with very different kinetic setup and all that, right? And you're often going to see like there will be a lot of collaboration that kind of jump in and start to calculate such a quantity. And so what you're going to see is there will be various different collaborations, and they will have various different kind of numbers. And then how do you kind of compare them together? You are not a lattice person. You just like, oh, I want to use the number, for example, right? And so we started this workshop called Lattice PDF series in 2017. They're going to be one here in November 2014. But one of the things we do is, we come into the same problem. Our colleagues, phenomenologists and experimentalists come to us like, I want to use the latest number, but they're all different. So how do I choose, right? So one thing would be nice to do some sort of global average, like the particle data group, but we didn't do that because that involved a lot of latest politics as well. So at the end, we decided we just do a rating tables, and then we quote people's number here. And so what we did is we use some sort of standard that some of the latest people sort of agree on. You will have very different lattice spacing that correspond to something called discretization error, or how light your pion is, right? The lighter your pion using your calculation should give you closer to true answer, for example. Do you do multiple value calculation that might tell you about the finite value extrapolation? Do you do excited state analysis that tell us how well trusted your ground state is, and so on? And so we come up with this rating system is something that's well under control. We give them a star. And things that may not be studied or only say, for example, you only have one lattice spacing, and then we give them a ray star because it haven't been really estimated there. And then something in between might be okay, we give them a circle, right? So in that way, it's like a rating system, even the kindergarten can understand star, it's good, ray, it's bad, and so on, right? And so there will be some discrepancy, like I say, right? All these numbers should be, these numbers coming from different gauge and fermion action, which have lattice spacing dependence, right? And the value and all that. So it's only agree when you do that proper continuum extrapolation. Before then, they can vary just because they have a different choices or action and everything, right? And so we see some discrepancy. It's nothing to alert too much until they have all the systematic under control and they still disagree. And that's where we need to worry about, right? And so for the tensor is one of the things that we find is sort of like I say, it's much harder to do this from experiments. So there are a number of people, some in the community, they do something called global fit. So what they do is they take various different experiments, try to combine them together, and they come up with best estimate they can. So in this case, in terms of tensor charges, is not quite well known, but this calculation actually can provide pretty reasonable estimate. We can even look at the flavor structure individually for the up quark, down quark, and strange quark, for example. And so that's why they become really popular on the lattice community, right? Because now we have something that we can actually contribute to the hadronic physics community that's more unique. And so one of the things I did with some of the people here, Wally and Zeto. So this is from a few years ago, but we are trying to use the latest tensor charges, which only give us a number, which is corresponding to the integral, basically integral of the PDF, right? Parton distribution functions. And you can do the same using experimental data. So for example, we do a subset of data, something called semi-inclusive, deeply inelastic scattering on the pi plus minus production data to try to extrapolate the parton distribution function, so up quark contribution and down quark contribution. And without the latest inputs, so you get this a little bit larger error band in the yellow zone. And when you implement in the latest calculation, which is the area basically between the up quark and down quark, right? But it doesn't tell you the shape. It give you it constrain the number, the area between the up quark and down quark. It doesn't give you the shape. Experimental data tell you the shape. And by combining available experimental data and the latest number together, we get a much better prediction for up quark and down quark itself, right? And then as a side product, there are also improvement in something called fragmentation function. That Lattice QCD cannot calculate that. That's one of those dynamic change property that using the Euclidean space is not very good at calculating. And so there are a lot of these very nice, interesting applications outside the lattice itself, right? Okay. And another reason that people get interested in, and also my colleague and myself spend a lot of time trying to improve the charges is one of the motivation in the beta decay. So we all know roughly about the beta decay. So they traditionally have this Fermi constant, and you got the traditional vector minus actual contributions, right? But if there is beyond certain model, there could be other contribution at a lower energy, right? So that could come in from like operator, like a scalar operator or a tensor operator. And there at the low energy, the quark contribution corresponding to the charges that we don't know, we can quite measure very well experimentally. And so this comes in, and then they couple with some of the, like a parameter, just like similarly with the Fermi constant that give you the W boson masses. This coupling constant give you some information if there are new particles out there associated with the strange scalar and tensor properties. And that's coupling constant will tell you the magnitude of that. And then we can tell our LHC colleagues that, oh, there might be some particle around these mass ranges that you can look at, right? And so this is in combination with, we're looking at some sort of very difficult measurements in the neutron beta decay. And they are very different quantity that, that goes into the beta decay that we can, in principle, measure with the combination of lattice inputs. And so this is kind of the one of the work we do. In short, is we sort of having some of the observable that coming from precision low energy measurements, combining with the coupling, and we are hoping to map out these epsilon parameters. And that with the experimental constraint, we can make out like roughly where those coefficient would be, and then somewhere that, and then in comparison with what their current LHC capability, and then make some prediction there as well. All right, and then there are other things, more complicated thing that you heard people call it disconnected diagram, is now you can have an operator sort of cell contract with cell and only interact with your other quarks through a number of complicated vacuum gluon loops. And this kind of calculation become more complicated and numerical more intensive as well to get a good signals. And so again, we do some very similar things. So I don't want to get into too much detail there. So you have to do the same. There are two kind of contributions. One is the continued, what we call kinetic contribution, where you plot directly in one of the quant lines, or you have this disconnected contributions. And then there you can kind of study the individual flavor, how much of the spin that's coming from by quark itself, right? So you can make out the information and help us understand where what the quark composition comes in. And then we can do the same thing with tensor charges. Again, what we do is changing the operator, and you do very similar exercise. And then there, again, you can make out the individual tensor charges from very different quark flavor as well, right? And one of the application we are particularly interested in this case, is the electric dipole moments, right? So some of you might have heard of something called CPU violating effect. One of the reasons that we still exist rather than have a universal matter antimatter in the universe because of such symmetry breaking. Therefore, they are more matter than antimatter, and we exist, right? And this obviously is a very, very small number. And there are a lot of experiments that's going on. Unfortunately, some of them got killed by the DOE in the US, but they are still, in Europe, they are still really looking into this experiment as well. And so there you can also write down some, just based on operator regulation, you can write down a number of basic QCD one and a few of the non-standard model existing ones, and you can try to find out, again, try to find out the coupling constant that give you some property related to new particle scenario and so on, right? And there, so there again, you need the coupling from individual flavor, and then we can combine with various different experiments. And then we can say some upper bounds in terms of, say, if split model, for example, Huey-Wen model is the right new physics model out there, and we should see the dipole moment should be smaller than this number. And if not, that should rule out those combinations. And so again, sorry, this is a lot of material, but the main takeaway is that, yeah, yes, even though we study very fundamental QCD property, those fundamental constants can be combined with other effective theory and do more beyond just QCD application itself, right? And that's why I really like about some of our calculations. Right, okay. Any questions so far? Yes. Oh.
Hello. So way back, you had your plot, your tables for your ensembles. And I was just wondering, it's a small question. On the right-hand side, you had the number of calculations. You had two colors, red and green. I just didn't know what they meant.
Yeah, sorry. So this was meant to compare with the earlier ones. So, so we have done this calculation for many years to try to pin down all those calculations. So the green one is the updating numbers in comparison with the older numbers. Yeah.
Okay.
Any other question?
Yeah. So the main really takeaway here is the number of measurements. So when we do, so the most precise lattice QCD calculation is like the pseudo-scalar decay constants that we can do very well, sub% for QCD quantity, which is very, very rare. Lens, but even in those cases, they don't really need as much measurement as we do here. Like people usually, there a few thousand measurements and that's sufficient. And for us to get down the nucleon coupling, we need to invest a lot more resources and computation to do the calculation. Yeah.
I had another question.
Oh.
So for the baryon matrix element slide, you can go back there.
Which one?
When you show the baryons and they have the quark lines and the insertion of the current.
Yeah, am I going the right direction?
I think
No.
backwards. The two of them.
Source and sink.
Yeah.
A picture of the source and sink.
Oh.
Okay, yeah. So for this insertion here, you say, do you have to put it at various time ranges? Like, how do you constrain the time ranges? And you have it only on this red one, but in practice, it can hit any of them, right? So how do you design it so it doesn't discern?
Okay, so you had to imagine this is a 4-dimensional, grid, which I did not plot, right? So you do have our time is discretized, right? So there are only certain number of time as a function of as a constant of the smallest lattice spacing, right? And so this time would be really just on the anything in between where I put the source and where I analyze in all the possible time. Yeah.
Okay, and is there temperature in your calculations?
Yes, a good question. So all my calculation is what we call zero temperature calculation, that we usually make the time extent much larger than the spatial ones, so we don't have to worry about thermodynamic effect. Yeah. And
do you use open temporal boundary conditions?
I need to check, but I think we do anti-periodic for the time. But they, like I said, they are at least twice as large as the spatial one, so we don't worry about the finite temperature effect. Yeah.
All right, thank you.
All right, so I hope to finish this in 10 minutes, and then we can do some hand-on exercise. All right, so those are the couplings and then some of the applications, and they are very different structure. We do also study, right? So there are something called structure, which corresponding structure function, which corresponding to various different distribution functions. And they are like a little bit like a one-dimensional structure. They usually give you a number only, and then they are experiment process such as the inelastic scattering experiments that can give you some of those information. And on lattice, we can calculate those what we call moments, which is integral of the distribution function directly, right? And so they are very, very different type of such a calculation. We have a more complicated operator now. And the same process, you create particle, analyze them, and you put in this particular design operator for those. And then, so in this case, we can look at the up quark and down quark differences in terms of momentum fractions. Again, we repeat the calculation, do a simultaneous fit, and to get where the true continuum limits are, right? And okay, and then you can also, again, you can compare with various different glue. You can put on the same rating, and then you can also compare with a global fit. And what we often find is in global fit actually do better with for the lattice because well, we started DIS and SLAG about 1960, so there are actually a lot of experiment data out there. So they actually do better than what we can do on the lattice for now, right? For the up quark and down quark flavor. But when you start to turn on, and then, yeah, so this is another way to look at all this collecting data. The green point corresponding the data from the global fit to combine with a lot of different experiments and some of the latest calculation. And there are also cases that one can, but then in the cases when you start to turn on the polarizability, when you require polarized structure, which is sometimes require you have a polarized target or polarized beam, there to set up is much more complicated experimentally, right? So the global fit there often require a more very different assumption sometimes, especially when the data is not precise. And they all have been some theory collaboration, try to understand the underlying theory to come, how do you combine different experiments also become a lot more complicated. And in those cases, lattice calculation actually remain about the same. So we actually can turn on the polarizability by having a different operator that have those properties. And there the calculation is similar. And then you can see that the lattice result involving polarized structure that become much better compared with experiments, right? So there are some complementability there that one can actually interplay between lattice experiment. There are something that is we have tons of experiment data, and lattice doesn't have enough resources to compete for the moment. But there are also quantity that we can do much, much better. And experimentally, we don't have a lot of experiment data to play with. So there are definitely some complementary thing that can go on here. I'm going to skip that one. And then you can also look at some sort of two-dimensional structure, things like form factors. And there are a lot of elastic scattering experiment going on. And the most often one that we study in terms of proton structure would be like something called Dirac and Pauli form factors. Or if you exchange a in the actual charges cases that you can, or neutrino scattering, instead of electron scattering, you can have axial and pseudoscalar form factors there. And there you kind of try to study this Q square, how much of the momentum being transferred in the process, right? And so they just have been doing this for a long time. And more recently, it's like this is all the number collected from something directly calculate physical power mass, right? It's something we do very well. We have reasonable signal control and then a lot of different glue, which indicate in different color, different flavor, depends on their interests. And then we all have some, this is an electric form factor, this is actual form factor. We have lots of those calculation that directly a physical power mass. So we kind of eliminated at least one of the systematic that could be introduced in the system, right? And so we have a little bit of exercise in terms of thinking about some of this. We can get to that later, right? And okay, I'm going to skip that as well. And with the form factors, you can also try to visualize how using the form factor, you can fully transform them into the impact space and kind of try to visualize how the proton and I think this is a proton and neutron, how they might look like structure-wise in the two-dimensional plane, right? And then we can also look at like strange quark, for example, strange form factor. Again, that's become more difficult to measure. And I think there's still experiment going on in JLab. When I was postdoc here, there was a big Q-week experiment trying to measure the strange form factors. And this calculation actually can do better for the strange form factor than available experiment at the time. I don't know about today's status, so go ask the question tomorrow when you're on the tool. And there are also things like hyperon form factor. That's something I did here, or with a number of scientists here. And there is just, the difficulty is you don't really have a stable hyperon, right? So for example, right? Sorry, wrong direction. Right. So for the proton and neutron, it's a little bit easier because you can get the proton target, you can make them, and you can just scatter them and can study them. For hyperons, because they decay so quickly, and so you can really do that very well experimentally. And again, so that's where Lattice QCD can do much better as well, right? And then you can try to really make out the three-dimensional structure. So there are a lot of effort today that's focusing on something called generalized parton distribution functions. There are a number of theory collaboration that's focused on such a quantity as well. And there are lots of experiments here that can contribute to this quantity as well. And the nice thing people really like about them is, so now we can actually see better what that mysterious object in terms of what we want to know is proton, neutron, some fundamental particle, not just the two dot here, but you can really make out those structure. And a lot of quantity that we studied before, if we know what their generalized parton distribution function is, there's a nice connection to, they are like this weird new variable introduced. you can connect them to those variables as well. And they can give us additional information rather than just a very nice mathematical definition that cover everything else. It can give us some of the information in terms of how the spin composition look like inside nucleon. Well, we look at a little bit of quark before, and then they are also like how the gluon contribute and how the gluon interact with the quark inside the proton that contribute to, say, spin and the masses. And then they are also very interesting going on. Like people are trying to study the proton pressure now. That's, again, big experiment going on in, I think it's hole B. There might be more experiment at different holes now. So do find out more tomorrow and you can tell me. So, oops, that doesn't turn out well. Yeah. So again, right, we are doing this, the same thing. We have protons, we have particle create and analyzing in certain space-time. Now we just have, slightly more complicated operator, right? And this matrix element, not just a very simple quantity that they are actually coupling with multiple form factor. Now we had to kind of vary the momentums, vary the different indices so that we can solve for those individual form factors, right? But that's something that we can work out. That's no problems. And so this A here at the Q squared equals 0 goes back to that momentum fraction that we saw in the one-dimensional structures. But there are additional quantity that combination with the A and B form factor, the Q squared equals 0 give us some of the spin contribution. And that can be gluon quark along or the gluon contribution as well. And one of the things you're going to probably see some poster in the hall, or probably somewhere here, you can probably see in the hallway is the pressure and the shear spreads that we can also calculate on the lattice, right? So there's a glue at MIT. They have doing this and they have been kind of continue pushing that precision. They're doing very well calculation. So this quantity is a little bit hard to extract. So you need like a lot of statistics and you can study the Q squared dependence. From the Q squared dependence, you can try to study Fourier transform them to some sort of distance space. And there you can connect that with some sort of pressure mag inside proton, which their result end up on the cover of the PRL, which is quite exciting, right? And similarly, you can also, now we can try to think about where the spin come from. In addition to the quark spin by itself, which is from the couplings, you can also have like quark orbital angular momentum contribution. And then you can basically cut this pie to know the total spin should be 1/2. How much of that coming from up quark? How much of that coming from down quark, strange quark, and chub? Or how much of that is intrinsic quark? How much of that is coming from something more complicated? And there are there's actually very few calculation here because the work involved here to decouple the quark and gluon become more complicated. And so far there are 2 collaborations that's doing such work. And some of them is not even near physical biomass. It's quite heavy, just sort of indicating that how difficult such a calculation is. Yeah, actually I should mention this calculation also done somewhere about 400 MeV as well, because I say this is a very small noise in quantity. So people can get quite good signal at physical biomass yet. And similarly, you can also look at the proton mass decomposition. You have various different operators and they can make out where the individual contribution. And sometimes people study the biomass dependence as well and so on, right? Okay. So with that, is there any questions before we move on to, yes.
I don't know how much this is relevant, but still, as a theorist, I'm just trying to connect this to the QCD phase diagram. So as you said, like at low T values, right? Like these all calculations are at low T values, temperature?
0 temperature, yeah.
0 temperature. And what about the baryonic chemical potential? Because in the QCD phase diagram, we have it like temperature and baryonic chemical potential. So what regime this will fall for mu? I mean, the baryonic chemical potential to temperature ratio, like?
Yeah, so now my presentation here covers those areas. So there's a spatial sub area that what we call thermodynamics of lattice QCD. So there they will vary the temperature and they will study their specific quantity corresponding to various different quantity that you're familiar with, the thermodynamics. So there they do try to vary those and they are, it's a whole another set of talk there, yeah.
Because actually it's like mentioned sometimes when we study the effective field theories that lattice QCD is not valid to very high baryonic chemical potentials yet.
Right. So I mean the baryon density, right? That's why you interesting.
Yeah.
Yeah. So the baryon density is sort of that so we calculate something that's like a equilibrium state or the statistic, right? And so so when you try to put in, like this is the reason I didn't cover here, but you see a lot of results only proton, nucleon, right? You start to put in more nucleon in our QCD vacuum. And also why we need a lot of statistics because the QCD vacuum cell doesn't like, we basically couple better with the zero baryon density state. So when you start to put in one nucleon, that's okay. We can kind of beat it with a lot of clever tricks and statistics. When you put two, things will get more complicated. And you put 3 and 4, that's become really complicated. So if you are seeing some of the calculation that's done using nuclei, that usually done on much higher masses. Early days about 800, and then to recently probably 300-400, because you had to fight that noise because it's like you are playing a card game and the dealer have the upper hand and you always lose. It's a little bit like that. I did some of those calculations. I feel a little bit like that, right? So you don't have the QCD, the background itself doesn't like it, so you get a lot of noise. And there's a lot of number of tricks that people think I haven't mentioned here, but a lot of time, like yes, you can always just sit back and wait for computer to catch up and do the work for you, right? But a lot of time people are thinking about how do you beat that odds in a way, right? That's where the theories come in and think about various different tricks, different operator, different way of getting that right. So yes, so in principle, it's not the most ideal method to do the finite temperature, finite density. Finite temperature is okay, finite density is more difficult. So what people do is we do small perturbations, right? So I can deal with small baryon numbers. I can, the perturbation basically like a tidal expansion. I expand say I have a small baryon density, I can tidal expanding them and I will calculate them, fitting them like a fixed way in my vacuum, and I can do a few of them. And you can imagine that doesn't go very far. You go, get as baryon density large, you can't do that anymore, right? Another region that people have calculation is super large baryon, right? There you will be instead of expanding in terms of baryon density, you expanding in terms of 1 over inverse baryon density. Again, there's all the trick that people do, right? In the quark physics, we either expand in small quark physics, small quark masses that become chiral physics, or heavy quark physics, you expand in terms of 1 over the mass of the quarks, right? Same thing here. People can also do super large baryon density by expanding term in terms of 1 over baryon density. So there you can also get something there. So there's this gap from very small and very large, and somewhere in between, nobody quite know what to do. Similarly, like a chum quark physics, like it's not heavy enough to be a nice heavy quark expansion theory. It's not light enough, they can use chiral quark. It's a little bit like that. There's this region that we don't have much information there. Yeah. So there are some limitations that what we can do. Mm-hmm.
So for your studies on DIS or CIDIS, you treat the current coming in from the electromagnetic probe locally. Have you seen there to be any need to distinguish the quarks in terms of the charges? Because I see you do NF is equal to 2 + 1, so they're degenerate. But is there any need for precision to include them to not be degenerate?
All right. So let me go to the other. Okay. So the vacuum, right? So in early days, like I said, most of the QCD quantity are pretty noisy, and then I think where do I mention that? Yeah, right. So most of the QCD quantity that we really don't know as well, right? A lot of isospin breaking, which in terms of aqua masses and non-quark masses, is expected to be somewhere below 1%. So if you are looking at the quantity very precise, they might become important factors for you, right? And so for us and for most of the nucleon quantity, we haven't get quite there yet, so it wasn't a big concern. But there are actually people who are doing 1+1+1 gauge simulations. And they was particularly, they use those gauge particularly try to study the isosymmetry breaking there. And that they can pull some of the information there. And I mentioned here because it's a little bit easier to think about it rather than that, yeah. But there are people thinking about 1 + 1 + 1 and 1 + 1 + 1. Yeah, so it's doable, just sort of more complicated, more computational resources dependent, and you want to use them for good physics, right? Something sensitive to those effects. Otherwise, it's just a very expensive way of doing the same calculation that we can do from here.
Okay, thank you.
Mm-hmm.
Questions? Like there are
Maybe we can
questions missing from this side.
take a break, take a quick break, and then when we come back,
That
we
works.
can try to see we can form slightly different group from yesterday, if that's possible. It'd be nice to get you guys are going to see each other for another 2 weeks also, so we can have a slightly different mix if it's not too complicated to arrange. And then you can think about, oh yes, our new question today. All right,
That's good.
Ah,
Let's thank Professor
everybody move around.
Huey-Wen.